welcome guys to yet another video on physics stuff, and today we are going to talk about optics. A really big topic, I would say, but we are going to go through a set of principles which we are going to first introduce, and then we are going to try to explain why exactly those principles work, and then we are going to move into deeper stuff like photonics and how photonic integration works. But first we have to very fundamentally ask ourselves the basic stuff, like if light is a wave or light is a particle, how does light work in basic stuff like refraction, diffraction, at the boundary of surfaces, and what really goes on in the entire thing with light. So today's video is going to be about if light is a wave. It's really a discussion that has made scientists ponder since the age of Newton, I would say, since the age of Huygens. It's a long story that has been going on for a long time, and it was a bit here and there because first people thought it is a wave, then the corpuscular theory came by, and people thought, okay, it might be a particle, but then there was a proof of it being a wave, and then again in the 20th century we had a couple of proofs that light was indeed a particle. But yeah, today we are gonna just talk about if light is a wave, and we are gonna ask the first questions as to why it could be. Right, so the first question that we ask ourselves is if light is a wave. So before going to that, we have to first understand what really is a wave. Sometimes in physics or in any science in general, it is, again, my opinion that it is very difficult to explain the simple things once you delve very, very deep into things. And we have to very fundamentally, again, ask ourselves what really is a wave. If you think about it, I'm going to also write along with it. Wave is basically a dynamic disturbance of one or more quantities that is propagating. So what it really is basically a disturbance, and by dynamic it obviously means that it is moving or it's changing its state. And of one or more quantities basically means that some of the other quantities is basically changing. Like if you have a water body, a surface of a water body, then if you drop a stone, you generally see waves. What basically changes is the quantity of the water molecules, let's say, over a period of time at a particular place. And what we really see is basically the distribution of energy that changes in space. And in case of light, what we all know, and if you do not know, first just assume that you do, and then we are going to anyway delve deeper later on in the next videos. But for light, it's basically a dynamical disturbance of the electromagnetic field. And yes, you're right, the electromagnetic field that also considers electric charges like electrons, protons, and stuff like that. So the very, very basic electromagnetic field. And we all know, or if you do not, again, just assume that you do, that if we have two coordinate axes for the room coordinates, then generally we have an electric field that goes on like this, an electric field wave, and then we also have a magnetic field wave that goes perpendicular to it. I'm not very good at drawing. And light is basically an electromagnetic wave. An electromagnetic wave, whereby you have to understand that the electric wave, it swings in this direction. The magnetic field, it swings in this direction. And light is basically perpendicular to both of them. So if we say that the direction of light is in this, direction, which is basically a k vector. So a k vector will be perpendicular to the electric field as well as will be perpendicular to the magnetic field. And it is actually crazy knowing that light is so fundamental to our universe, and it is yet again very, very fundamentally connected to the electromagnetic field. Why is this so, and why we came to that conclusion as humans? We will talk about that later on. But first, we just ask the more fundamental questions. So what are the properties of waves that light inherits? So waves have particular properties, like if you consider a sine wave or a cosine wave, it always has certain properties. And if we delve now very much into the basics, if we again have these two room coordinates, whereby we take the x-axis as t, so time, and the y-axis as some variable a that basically changes, because again we need some quantity that changes, that dynamically changes over time for us to have a wave. And what we basically do here is that we first take a wave, again I'm not very good at drawing, so pardon me in that case. But consider this as more of a sine wave from the trigonometric function of sin or sine. And we have certain characteristics here. We have firstly the height of the wave, which we call as amplitude. Then we have the distance between two hills or two troughs, as we call. It's called the wavelength, and it's denoted with the Greek alphabet lambda. So first of all, let us mark out all the properties that we are talking about. The A0 will be called an amplitude. The lambda, the Greek alphabet lambda, will be called the wavelength. We also have the linear frequency, which is denoted by an F or a nu, also a Greek alphabet. It is 1 divided by the wavelength. So I'll call it the linear frequency. So now it might be asking, why do we call it linear? Is there something that is not linear? Yes, you also have circular frequency or an angular frequency, and that is denoted with the Greek alphabet omega. And it is basically 2 pi f, or in other senses 2 pi divided by t. And what really is t? I have made one mistake here. This should actually be t, the time period in which the wave goes to one wavelength. So I'll just also write it here. T is equal to time period. And yes, now it all goes perfectly. And this is again called angular frequency. A very, very important formula here is that the speed of light, which we call c, as in the English alphabet c, nothing fancy here, is actually the wavelength times the frequency. Right. What else do we have here? We can also write the wave vector, which is denoted by a k. I'll also write here that this is the speed of light. And k is called the wave vector. And the wave vector is basically 2 pi divided by lambda, the wavelength. So it basically means how many wavelengths are there in one complete cycle of 2 pi of the wave. And the vector version of the wave vector, what we have written here, is basically the not so vector version, and it is also actually called the wave number. Let me correct it here, the wave number. And the vector version of the wave number would actually be the wave vector. that we were talking about. So it basically gives us the direction of the wave. So we can also write that if it is a sine wave, as in our case, we can always write the sine wave as something like this: omega t plus or minus phi, which is another Greek alphabet, and a0 on this side. And we can basically write this formula here, whereby you can very well understand that this part here is the phase, and here it is the phase difference. What is actually the phase? The phase is basically where it starts from, like the wave. If we think of it as like if the wave starts from here, then we see that there is a difference in the starting point here. So the at t equal to 0, the wave will not have the value of 0 anymore, but some initial value which is here. And that will be basically the phase difference of the wave from its ideal position, which is at 0. Right. We also have the concept of wavefronts, which was introduced by, I guess, the Danish, the Dutch, I don't really remember that much, scientist Christian Huygens and Augustin John Fresnel. Actually, almost like decades apart, centuries apart, I would suppose. What Huygens basically first did was to introduce the concept of wavefronts, and Fresnel basically extended it and proved it with respect to interference. And that's why this principle is called Huygens-Fresnel Principle. And what does it actually mean? It means that the waves that we saw before basically form these very abstract concept of a wavefront. And wavefronts are basically these surfaces, these planar surfaces, which move along with the wave. And how would one really think of a wavefront? It is, well, how you would consider the waves with points in the waves which have the same phase, and they move along with the wave, and these points of the same phase would be the wavefronts. Right, so basically these are surfaces which are related to the same phase of the wave. As you also see in this picture, always the highest points of the waves are taken, and they are called, they are assigned a wavefront. So basically all these wavefronts are similar, and the distance between them would also be lambda. So this is a very important thing for wave optics. Even in its inception, it was pretty much famous because it could explain some very useful phenomena which were there in nature. And talking about useful phenomena, the first thing that we have is diffraction. And before we again get into diffraction, we have to analyze yet another point in the Huygens-Fresnel principle, which is that every point, that is what the principle says, every point in the wavefront can give rise to a new secondary wavefront. What does it mean? It means that if you have a wavefront here, and if you take any random point, it can give rise to yet another new wavefront, and which is mostly spherical. Why? We would also talk about that in a later video. But this is another point of the Huygens-Fresnel principle. And in diffraction, one uses this very nicely. What basically happens in diffraction is that you send light through a slit, so a very, very tiny opening, and you get wave-like behavior out of it, as in like it spreads apart, and it spreads apart in the room, which was previously not the case. In the previous case, you would have put a screen in front of the light, and you would have seen the entire screen getting illuminated by the same intensity in all points of room. But after passing through a single slit, it is not really the case, and you have a different intensity graph. And what basically happens is that each point, like basically when you see the wavefronts here, they go and hit a slit, and most of the light is actually blocked. But then if you imagine some of these points, within the part of the light that is not blocked, they, according to the Huygens principle, will also create new wavefronts. And what really happens is that they overlap all these waves and they create a bigger wave like this. And that is why you see the bending of light at the corners of these openings. Right, so we have diffraction and then we also have refraction. Refraction is basically a phenomena whereby light is hit on the boundary of two surfaces which are different in terms of optical density, and then you have a bending of the light ray in comparison, like the angle it changes with respect to the normal, which is basically orthogonal to the plane of the boundary. So for example, this here would be the normal here, and you see that the light, it hits here and then it deviates a bit, and this angle basically reduces here. Why this happens, we'll again talk about it later on, but it is a very fundamental phenomena to explore the concept of refractive index, and that is a really big part in optics. And but what is in its core is basically the change of direction of light and also the change of apparent speed. If it is so or not, we will be talking about also in a later video. But what we can do here is that we can explain this also through the Huygens principle. And is there any proof that light is actually a wave? Well, yeah, the Young's double-slit experiment in 1801 did prove it, which was basically a similar experiment which we saw earlier with a single slit, but this time with two of them. And you see the fun in this situation, because when you have two of them, the waves basically overlap, and when the waves are not in the same phase, then you do not have an interference that gives the wave a strength, gives the intensity a strength. So basically you have the concept of constructive and destructive interference, whereby if two waves, if you consider two waves which come over at the same phase with basically no phase difference, then if we add both of them up, they will basically become a stronger version of them, of each of them, and this we call the constructive interference. If in case, however, there is a phase difference, and let's take the worst of cases, that they are absolutely 90 degrees far apart, so which would mean that they are dynamically the opposites of each other. So you have a hill here and a trough here, a trough here and a hill here. What if you add them? And once you add them, you basically get total destruction. So you basically get no wave at all, so like a zero line. And this is called a destructive interference. But life is of course not so black and white, and it doesn't happen just like as in like 1 or 0, 1 and 0. It happens as a gradient, and what you basically see here is also something like that you have sometimes constructive interference and sometimes destructive. It depends on which wavefront basically interferes with which wavefront from the other slit. And yeah, so that was one proof that light is a wave. There were also proofs of the fact that light is a particle, but we will not be getting into it in this video, in a next one for sure. And I'll end this video with a nice video from another creator. I'm gonna cite his source, cite his website in the video, and it is basically a 3D rendering of the Young's double-slit experiment. And with that, we'll meet again in the next video. I hope you learned something from this video. Bye-bye.